All right, so we're going to start on section 6.6 in our textbook. So we have started with a Boolean expression and we have generated a truth table. And we've also started with a Boolean expression and generated a digital circuit. And I am pretty sure that given enough time, I could start with a digital circuit and I could generate a truth table. We said that I would map out all of the individual combinations of the original variables, and then I would map those one row at a time through a digital circuit, and I could generate the output that would be on that row for the truth table. Now, I didn't say it would be easy, I just said that we could do it. But is there any way that I can actually start with a truth table and work my way backwards? Can we start with a truth table and from there generate the Boolean expression that would create this digital circuit diagram for us? So that's what we're going to be doing in this section, is starting with a truth table. All right, so I have the truth table with the original layout for the X, Y, and Z. Because I have Boolean variables and there are 3 of them, that means that I should have 8 rows. To be as organized as possible, I'm going to toggle the first variable X, toggle 4 and 4, 1s and 0s, and then I'm going to toggle the Y 2 at a time, the 1s and 0s, and then I'll toggle the third one 1 at a time. And so given that particular layout of my original X, Y, and Z values, I am going to create an answer column that contains some values, and the question is, what is the Boolean expression? What is the function, the f of x, y, and z, that is generating this outcome? And is there a way that I can tell what that is? So this is the same output column that we talked about in class last time. So it's going to come back and we're going to see if we can find out the Boolean expression. There's actually 2 different ways that I can start with a truth table and move into a Boolean expression. And the first way is called the sum of products. The sum of products involves something called min terms. Min terms are a Boolean expression that results in a 1 for the output. So what I'm going to do is I'm going to look on my answer column and I'm going to see if I can find all of the values that are 1. And so I can see that this is generating a 1, and this is a 1, this is a 1, this is a 1. I have 4 1s in my output column, and I'm going to try to find the min term, or identify the min term that is generating that 1. Well, I know that here, if my input is x, y, and z equal to 1, so if I have an x equal to 1, a y equal to 1, and a z equal to 1, that my output column is a 1. The min term is this x, y, and z value that is generating that 1. So if x is equal to 1, I can just represent it as an x. If the y is equal to 1, I'm going to represent it as a y. If the z is equal to 1, I'm going to represent it as a z. So the min term that is generating that 1 is an x, y, and z. Let's go down here to this second one because it's a little bit different. Here I see the x is a 1, the y this time is a 0, and the z is a 0. Well, if if x is equal to 1, I can just represent that as an x. But now I have a y equals 0. What am I going to put here to indicate a y is equal to 0? That is actually going to be a y naught. It is not y. And since z is also equal to 0, that is also representative of not z, because the value in z is 0. So let's move to this third min term right here. I see x is equal to 0, y is equal to 1, and z is equal to 1, given the original values in the original 3 columns. So if x is equal to 0, that would be an x naught. If y is equal to 1, that would be a y. If z is equal to 1, that would be a z. So here is my third min term. I want to explicitly say that this is the product of these 3 variables. So it's actually x and y and z, but we can imply that multiplication just by putting the variables together. As we reminded you, we do implied multiplication all the time. If I have some variable 2x, the implication is that I am multiplying the 2 by whatever value contains in x. But I don't always show, or we don't generally show that multiplication symbol. So the same thing is applying to these three minterms. Speaking of minterms, let's do the last one. We have x equal to 0, y equal to 0, and z equal to 1, given the value in the three original columns. I'm going to find out what that minterm is. If x is equal to 0, that is an x naught, or not x. If y is equal to 0, that is a not y. And if z is equal to 1, that is a z. So I have 4 ones in my output column. I have 4 ones. That means that I should have 4 minterms. So I'm going to find the combination of x, y, and z that is generating the 1 in that output column. And what we're talking about is the sum of products. So as you might guess, I am going to sum all of the minterms together. So the first minterm is x, y, and z. The second minterm is x, y naught, z naught. The third minterm is x naught, y, and z. And then the fourth minterm was x naught, y naught, z. And I am going to sum all of these products together. And this is the Boolean expression that is generating this particular output. So this is the Boolean expression here that is generating this particular output column, the sum of products. But just because I have found the Boolean expression does not mean that it is the most simplified Boolean expression. So the next thing that I would want to do is apply our simplification rules that we learned in the last class, the last video. Apply those simplification rules to this Boolean expression to see if we can simplify it any further. Let's just count up the number of digital circuits or digital gates that would be required to do this. So how many NOT gates would this particular Boolean expression require if I was going to convert it into a digital circuit? Well, I see 2 here, 1 here, and 2 here. So I am going to have 5 NOT gates. How many AND gates am I going to require? Remember, an AND gate is an implied multiplication. So there are 2 here, 4, 6, and 8. So there are 8 AND gates. And then how many OR gates? Remember, the AND gate is implied multiplication. The OR gate is addition. And I can see 3 plus signs. So altogether, I have 16. It's going to require, if I leave this Boolean expression as it stands, there would be 16 logic gates on my circuit diagram. Now I can certainly see that this could be simplified. We're not going to go into that process right now, but I would look for common elements. I can see that if I were to put a label on this is the first term, the second term, the third term, and the fourth term, I'm looking for common values within each one of the terms. I can see both 1 and 3 have z's. 1 and 3 also have, oh nope, that's an x naught. I can see that number 3 and 4 both have x naughts, and so I could factor out x naughts. As a matter of fact, 3 and 4 also have z's, which means I should be able to factor out an x naught and a z from terms 3 and 4. So I would look for common values within each one of the terms that I could begin to factor out to simplify this. But we're going to move on to another example of sum of products. All right, so I'm going to have a truth table that's made up of 3 variables. Because I am using Boolean variables and there are 3 of them, there should be 8 rows in my truth table. So I'm going to organize it as much as I possibly can, as I've stated before. If you, as a programming student, prefer to start your toggling with zeros and then go to 1, your output column is just going to be upside down from mine. So let's say that this original order of x, y, and z values is generating this particular output column. So what we want to try to do is to find the Boolean expression that is generating this particular output column. So once again, we are going to look for the min terms. And the min terms are products of the original x, y, and z value, or the input variables, we have 3 of them here, that are generating 1s on the output column. And so I'm going to look for 1s in the output column. I can see that for this particular example, we have 5 1s in my output column. So I'm going to see if I can identify the minterm that is generating each one of these 1s. So let's start here. The way that I identify the minterm is I look for the x, y, and z value. So I see x is equal to 1, y is equal to 1, and z is equal to 1. And the minterm that is doing that, if x is equal to 1, it gives me an x, I have a y, and a z. So let's look at this, and this is the minterm that is generating that 1 in the output column. Here's my second one, where x is 1, y is equal to 1, and z is equal to 0. So if x is 1, I represent that as an x. If y is 1, I represent it as a y. But now I have a z equal to 0. And so the only way that I can have a z 0 is I am going to not the z. When z is equal to 0, that means not z or z naught. So let's look at this one. I have an x equal to 1, a y equal to 0, and a z equal to 1. Which means I have an x. This time I'm going to not the y because y is equal to 0. And then I am going to put the 1. So we have 2 more. This is x equal to 0, y equal 1, and z equal to 1. So this would be x naught, y, and z. And then my last minterm right here is x equal to 0, y equal to 1, and z equal to 0, which would be x naught, y, z naught. So there are 5 1s in my output column. There should be 5 minterms. And I am just going to sum those minterms together. So that would be x, y, z plus x, y, z naught plus x, y naught, z plus x naught, y, z plus x naught, y, and z naught. Hopefully I transcribed all of those 5 minterms correctly. So let's count the number of gates. If I was going to take this Boolean expression and draw a digital circuit for it, how many NOT gates do I have? Well, I see 1, 2, 3, 4, 5 NOTs. How many AND gates? Remember, if a NOT is a tick mark, and AND is implied multiplication, then we'll do OR next, and the OR is the addition. So how many multiplications do we have? There's 2, 4, 6, 8, 10. I can see that I would have 10 AND gates. And how many OR gates? Well, I have 1, 2, 3, and 4 plus signs. This is going to give me 19 total gates in order to generate this Boolean expression, or to replicate this Boolean expression. Now, as I said, this is definitely not going to be the most simplified Boolean expression, but the point was, can I start from a truth table and end up with the Boolean expression that would generate that truth table? And we have found out using the sum of products that I can do that. I would definitely want to use the simplification rules to reduce this particular Boolean expression to use less gates. So I'd like you, for your turn, to look on page 250 in your U.S. textbook, on page 280 in the International Version, and I want you to find figure, this would be 6.71. That's going to be a truth table. In the International Version, that would be figure 71, on page 280. And what I'd like you to do is, given the truth table, I want you to find the Boolean expression using the sum of products. All right, so I'm going to put your confidence on here. I'd like to know what your confidence on a scale of 1 to 5 is for, we have talked about minterms and the sum of products. That's a P, sum of products. So I told you before that there were a couple of different ways that I could start with a truth table and move to a Boolean expression. So we're going to talk about the second way to do that, and it's called a Karnaugh Map. So a Karnaugh Map is going to help me generate a Boolean expression that is going to begin in a more simplified version than my sum of products would do. So let's just start with a simple truth table this time, something that just has 2 variables instead of 3. All right, so this particular original ordering of X and Y is going to generate this particular output column. And we just want to figure out what is the Boolean expression that is generating this output column. And so with a Karnaugh map that has two variables, I am once again still concerned with the min term. So I'm going to list out the steps to find the min terms. So the min terms, once again, are ones in the output column, or generating ones in the output column. I can see that I have an x equal to 1 and a y equal to 1. That is going to give me xy. I see that I have an x equal to 0 and a y equal to 1. I'm going to have to not the x because it's equal to 0. That will give me a y. So I have two ones in my output column. I should have two min terms. So the second thing that I am going to do is draw a Karnaugh map, and I'm going to map those min terms to my Karnaugh map. Because I have two variables, there are four possible combinations of two variables. I'm going to end up with an Excel spreadsheet kind of thing that's not horizontally straight. There are four possible ways I can combine two variables. I need four possible cells in my Excel spreadsheet or in my Karnaugh map. And I'm going to say that this particular axis is going to represent the two possible outcomes for x. And then I am going to put y across the top. So if you think back to your Excel spreadsheet, this particular cell represents where the x and y, the x and the y meet. This is x, and that would be where x and y naught meet. This is the x naught row, but the y naught column. Oops, no, not the y naught. The y column. And this is the x naught row and the y naught column. So I just kind of labeled those four cells so that I could remind myself what those cells represent. Now what I'm going to do is, the second step in the process is to map the min terms to the Karnaugh map. So my first min term is an xy. So I'm going to try to find the cell on my Karnaugh map that represents xy. Well, this first row is my x, and the first column is my y. So I'm going to put the 1 there. If you don't mind, I am going to delete those tick marks because they're making me think they are knots. So let me delete those. All right, so then my second min term is an x naught y, which means I need to find the x naught row and the column that represents y. There it is. So I should have two min terms, and that is going to equate to two ones in my Karnaugh map. I started with two ones in my output column. That translated to two min terms, which translates to two ones in my Karnaugh map. All right, so the third step in the process, I have to move my steps, I didn't give myself enough room, is to group the ones. Now, the nice thing about a Karnaugh map is that it is going to help in the simplification process over the original process of the sum of products. But there are some rules to the way that I am going to group the ones. So we're going to find out what the grouping rules are for Karnaugh maps. This particular presentation is available to you in your Canvas module, so you don't have to take pictures of it or screenshots. So let's talk about the rules that apply as I am trying to group the ones together in a Karnaugh map. First of all, I am going to, this is draw rectangles. I'm going to have a tendency to draw circles or something around the ones. But each rectangle has to cover 2 to the k squares. 2 to the first, 2 to the second, 2 to the third. You know your binary math. That means that when I am covering ones, I need to group the ones by some exponential value of 2. So 2 ones, 4 ones, 8 ones, 16 ones. I cannot just arbitrarily group 3 ones together. The next rule is that I want to group as many of the ones together as possible, remembering rule number 1, that they have to be groups of binary values. The next one is I want as few of rectangles as possible, which kind of ties back into the second rule, to try to group as large as possible or as many ones together as possible. The next one is I can draw my rectangles or my groupings horizontally or vertically, but not diagonally. So I can connect or group ones that are sitting side by side or top and bottom, but I cannot group ones that are explicitly sitting diagonal from one another. And we're also going to find out that the rectangles can overlap, which means that I can have a one or several ones in more than one group, because once again, rule number 2 says to draw the rectangles as large as possible. And then the last one is that we can wrap those groupings around the edges of the Karnaugh map. And I'll show you some examples of what this might mean. So let's come back to this Karnaugh map that we have here, and let's see if we can group the ones on the Karnaugh map. All right, so it said that what I'm going to do is I am going to draw circles, rectangles, that I'm going to draw rectangles around the ones. I have to group them in binary exponents. So either 2 or 4 or 8 or 16. Well, that's pretty easy because I only have 2 of them. It did say that I have to group them either horizontally or vertically. The nice thing is that if I had a 1 here, I would not be able to group them horizontally, but these are sitting top and bottom, so this is very nice. So I have grouped all of them together. I guess one of the rules that it didn't say is that all of them have to be in a group. Some kind of a group, they all have to be grouped. So for my simple truth table and my simple Karnaugh map here, it wasn't difficult to group them all. So the 4th step is to simplify. So when I say we're going to simplify, or I'm going to convert this Karnaugh map into a Boolean expression, I am going to say we're going to move through the group to find the Boolean expression that is generating that particular group. And the nice thing is that I only have one group here. So I'm going to put it in a red group. I'll put it in red. I only have one, but that's okay. So what I'm going to do when I'm moving through the group, I'm trying to find values in the group as I move from row to row, column to column. I'm trying to find values that do not change. And so just to try to be as organized as possible, I am going to move horizontally through the group. When I say I'm going to move horizontally, that means that I'm going to move from row to row to row. So as I move from this row to this row, is there a value of x? Because at the moment I'm only looking at rows, and the rows are indicated by x. Is there a value of x that's not changing? Well, actually, I'm going from x to x naught. So yeah, it changed. So when I move horizontally, I'm going to have everything that's changing. So let's try vertically. Vertically means as I move from column to column to column. Well, the nice thing is that I am never moving out of columns, so I am staying in a single column. So obviously that column header does not change, and so I'm going to put the y value here. So when I put this group together, this is actually going to equal y. And since I only had one group, this end up being the answer. The Boolean expression here the Boolean expression that is generating this particular truth table is y. That might be kind of simple to see because regardless of what the value of x is, my output column is always mirroring the value of y, regardless of what the value of x is. So let's try another one. All right, so I have we're just going to use 2 variables once again. And this time I'm going to say that this is 1, 0, 0, 1. So step number 1 is to identify the minterms. So once again, the minterms are the ones in the output column. I have 2 ones in my output column. This is going to be xy because both x and y are equal to 1. This one is going to be x naught, y naught because both x and y are zeros. So the second step is to map those minterms to a Karnaugh map. I'm going to do a shorthand called a K-map. which means that I need some kind of a table or an Excel spreadsheet. This is going to be my X column and my X naught column, or this is going to be my my X and my X naught row. This is going to be my Y and my Y naught row. I will tell you here that I can order these rows and columns any way that I want to, with one exception. I'm going to have one variable that's represented on one of the axes and another variable represented on the other axis. So if I had so chosen, I could have put the X and the X naught across the top, and I could have put the Y and the Y naught along the other axis. I could actually have even ordered my naught values, so I could have put X naught and X, Y naught and Y. So the way that I order my Karnaugh map is going to control the way that the Karnaugh map looks like once I have mapped the minterms to the Karnaugh map. But I just wanted you to know that the rules on drawing a Karnaugh map means that one of the variables has to be represented across one of the axes. The other variable would be represented across the other axes. The way that I choose to order those doesn't matter. As a matter of fact, I could have gone X and X naught and then Y naught and Y. So I can order these a variety of different ways. I'm going to have a tendency to do my Karnaugh maps this way, mainly because that's generally the way, starting with ones and moving to 0 is the way that I order my truth tables. So the next thing is to map. This is an XY. I need to find the cell on the Karnaugh map that represents an XY. Here is the X row and there is the Y. So I'm going to put the 1 under the cell that represents X, where the X and the Y intersect. The next one is the X naught, Y naught. So I'm going to put, this is the X naught row, the Y naught column. So I have 2 minterms, I have 2 ones. We have 2 minterms. I should have 2 ones on my Karnaugh map. So the third step in the process is to group the ones. Remember, if we remember back to our rules for grouping, I have to cover 2 to the 1, like 2, 4, 8, 16, 32 ones. I have to draw the rectangles as large as possible so that I can have as few as possible. They have to be horizontal or vertical. This is going to apply to the Karnaugh map that we're looking at. The groupings can overlap and they can wrap around the edges. So I am going to group this together. Let's do it in a different color. Let's do blue. So can I just group these 2 together? I mean, I have 2 of them, and you said it had to be some kind of a binary value, and 2 is definitely a binary value. Can I group these 2? Well, the answer would be no, I cannot, because I cannot group them horizontally. I can only group them vertically if they are connected or attached side by side or top and bottom, which means that I am going to have to group these separately. So I'm going to have a blue group and I am going to have a red group. I cannot group the 2 of these together because they are sitting horizontally. So I'm going to have a red group and then I'm going to have a blue group. So the third step in the process is to move through each one of the groups, simplifying it. The 4th step, I call it move through the group. So let's start with my red group. Since I have already written that down, we'll start with my red group. So once again, just to be as organized as possible, we're going to move horizontally and then we're going to move vertically, and I'm going to multiply those 2 or and those 2 outcomes together. So if I move through it horizontally, that means that I am moving row to row to row. Well, because this particular group never changes rows, the row that it happens to sit on is going to be X naught. I'm looking for values that remain the same and do not change as I quote unquote move through a group. Now let's do vertically. As I move through the group vertically, that means that I would be moving from all right, so we're going to move through the red group. I'm going to try to be as organized as possible. It may seem very, very simple here, but in the not too distant future, it's not going to be simple. Because as I'm moving through, I'm looking for things that are remaining the same as I move vertically through the row and as I move horizontally through the row. So vertically through the row is going to indicate, vertically through the group is going to indicate that I am moving from row to row to row to row. Given the fact that this group never even leaves that row, then the X naught never changes as I quote unquote move through the group. To move through the group horizontally, this might mean the columns. So if this is indicating how it changes as I move from row to row, moving horizontally is an indication of how I change as I move column to column. Well, because I never actually move out of this column, it would seem like this is going to be Y naught. So my red group is going to be X naught, Y naught. So let's check out my blue group. So my blue group, once again, I am going to move vertically and horizontally, and I'm looking for values, header columns and rows that do not change. So let's move vertically through the group. That would be row to row. Well, once again, because it never moves out of that row, the X is not changing. As I move horizontally, that would be column to column, but this group never moves out of that column, so the Y is remaining the same, which means that I have an XY. Then I am going to do the sum of the groups, all of the groups that I have identified, and this is ultimately going to lead me to the Boolean expression where I have the XY from my blue group. I'm going to OR that with the X naught, Y naught, the X naught, Y naught. Oh, I missed the Y. Did you guys mention that I missed the Y in that particular group? So this is going to be the Boolean expression that will be generated from the Karnaugh map. Now you may have already noticed that this is remarkably similar to the sum of products that would have been generated if I had just straight up used the min terms. That this Karnaugh map Boolean expression is no different. So I'm saying that the Karnaugh maps don't always generate the most simplified Boolean expression, but much of the time they can. All right, so your turn. Let's see if you're going to do it. I am going to give you a truth table, and from that truth table I want you to draw the Karnaugh map. From the Karnaugh map I want you to find the Boolean expression, and then once you have the Boolean expression, I want you to draw the digital circuit. So here is a 2-variable truth table along with an answer column, and from here I'm going to have you draw the Karnaugh map, find the Boolean expression, and then draw the digital circuit.